even potentially raising funding. And so what we're aiming to do when we get out of lockdown and actually can get out and do some stuff, well, we're out of lockdown, but when COVID releases us a little bit more, is to actually try and develop renewable energy projects and schemes. So, you know, we've done ask the experts on PV, and we're now looking at heat pumps, which is going to be one of the major, which Bean's going to tell you about, which will be one of the major inroads into getting rid of our direct gas emissions. The other sort of projects that we can think of to help get us to net zero. And in doing that, we'd like to support local community to get involved, either through share ownership or opportunities for local businesses to be involved in getting these projects put together. So again, it's trying to understand what supply chain that you put in, you know, can use and put in place to make things happen. So that's essentially what our objectives are. We are a few volunteers. Sorry, wrong button. We are just a few volunteers at the moment, and we'd like to have more people. So, as John said, very keen to take the princely sum of £10 off you to be a life member of Marlow Energy Group, to get involved. And we're keen to get people who are just keen to see things happen, or don't have to have expert knowledge, but any expert knowledge on any ways of raising money, doing projects, marketing, anything. We'd be really happy to hear from you. And to do that, then just get in touch via the website and Marlow Energy Group. So I think that's me done then, John. So if I stop sharing, and I think Bean can hand over. I don't know who's going to introduce Bean, but
you can, Dave. I'm happy to introduce Bean. Bean, please go ahead.
Right. Good evening, everybody. Has my opening slide appeared on your screen mysteriously?
Yep.
Excellent. Very good. Very good. If we start getting bandwidth problems at any point, perhaps people would turn their cameras off just while the presentation's on. If we have bandwidth problems, it's more likely to be my end, I must tell you, because everybody that should still be on the train coming home from Paddington is currently working at home in the village, and so bandwidth is a bit of a premium. But anyway, welcome, and first of all, I'd like to say thank you very much indeed for inviting me to give this short delivery on domestic scale heat pumps. So concentrating this evening on domestic, so household scale heat pumps. But that will necessarily include a little bit of a conversation on heat networks, where we are looking at multiple dwellings and ways of perhaps tying one or more properties together for maximum advantage. As they said very kindly in the introduction, I am currently the chairman of the Ground Source Heat Pump Association, but I'm also one of the founders of the New Heat Pump Federation, which is our new vehicle to broaden out the coalition that we're building in favour of the electrification of heat. That is deployment of heat pumps broadly, and the intent here is to try and build a body of businesses largely who come with such strength that government will have to start taking us seriously. So we're attracting people like Centrica, Octopus Energy, some seriously big names, many of the big players in heat networks and what have you. So, so that's just where we're coming from. So the first thing I would say is that this is where we need to get to. Most of you will recognise this. Our forebears recognise that our real source of energy is in fact the sun. So everything we're talking about in terms of renewables, with the one exception of deep geothermal, is solar energy. So it doesn't matter whether it's wind, it's direct solar PV, solar thermal obviously, biomass, all forms of heat pump, even drilled ground arrays down to 200+ meters, it is still stored solar energy that's stored in the crust. So we're not going down to the point where we're harvesting heat from the core. So the first question is, how many amongst you are actually own heat pumps at the moment? I can't see many of you, so I can't see hands up, but I suspect most of you go, oh no, I haven't got one of those. The fact is, most of you, well, I would say all of you have got at least one heat pump. Most of you have got two. Many of you might have three, some even four. So you've all got a fridge. Most of you got a freezer. Many of you will have air conditioning in your cars. So you're all owning heat pumps already. And the reason I make that point is that this is not something to be scared of. This is not a new technology that you should be worried about. This is something that you've already got in your homes. So why are we acting now? Why is this becoming that much more important? And I'm sure you've been through this many times with your group so far. But the IPCC report of the end of last year has given us limited time to stop irreversible damage. You don't need to read these slides. I think the intention is that they'll be published to you at some point afterwards. So this is really to remind me of what I meant to be saying. Current building regulations permit development that is adding to the problem. So at the moment, if you buy a brand new home, it's reasonable to think that it's coming at, sort of today's standards. Not a bit of it. Many of the new homes currently on the market are being built under building regs that are many years out of date. And that's a problem because nobody is being told that those new homes are coming with what will be a significant retrofit bill to get them ready for net zero. Public awareness is shifting rapidly. We've got generational pressure, so children are beginning to influence their parents, which is great. We've got the Greta and the Attenborough effect. So the biggest rock star at Glastonbury last year was David Attenborough by some margin. We have technologies available now that are tried and tested. As I said, heat pump technology, it's not new. It's been around for well over 100 years, and everybody already owns at least one. All the industry watchers anticipate a much more regional and distributed energy system in the future. So we're going to get away from having very significant, grids and move to much more regional potential. So we're going to make much better use of regional resource. And we've got this very rapid development of the electric vehicle market. Now, it's not massively taking off yet, but you can see where the direction of travel is. And by the end of this evening, I hope that you will be able to recognize that actually there's a narrowing of the gap between personal transport and personal comfort. Because if we move to electric vehicles and we start to move, and we're charging at home, and we're starting to move towards the electrification of heat with heat pumps, clearly those two things are narrowing and coming closer together. And by the end of this evening, I hope you'll see that actually there is going to be a very significant coming together of those technologies in the not too distant future. So what's held us back? And I think this is one of the questions that people probably need to have some view on is, why haven't we got lots of heat pumps already? Well, the simple fact is that we've had government policy since the 60s that favours North Sea oil and gas. That was seen as a massive asset, and indeed it was a massive asset. And successive governments have chosen to effectively give low-cost gas to the public for the last 50 years. By contrast, if we were in Norway, the Norwegians chose not to burn any of their North Sea oil and gas. They sold the whole lot, put the money into a national wealth fund, and now own something like 4% of globally traded stock. Unfortunately, we don't have any legacy like that to look back on from our North Sea oil and gas time. So at the moment, we have this massive spark gap. So this is the gap between electricity pricing and gas pricing, and the bar chart there shows the data from 2016, but it hasn't changed much. That we have the second highest electricity price in Europe, and we have the second lowest gas price. So clearly, there is a massive incentive to burn gas. What contributes to that is that all of the environmental levies are currently applied only to electricity. And the original rationale for that was that electricity used to be our dirtiest raw primary fuel, because most of it was generated by burning coal. But of course, that has changed massively, and you don't need me to tell you, I'm sure, how much that has changed over the last few years, was the growth in particularly offshore wind and solar PV. Nuclear power currently accounts for something in the region of 20% baseload in the UK, but we have some days where wind power is already generating nearly 50% of our electricity. So that's changing massively, and we have a lack of robust fossil fuel standards for the environment. At the moment, we're very poor at the way that we manage the deployment of fossil fuel units. So, to give you an example, the introduction of condensing boilers was seen as heralded as a massive step forward in the efficiency of fossil fuel boilers. Unfortunately, the introduction of the boilers, and they came with subsidies, which many people have forgotten, they didn't come at the same time with a requirement to control the return temperature to the boiler to ensure that they condense. So many condensing boilers actually never enter condensing mode, so we are not getting the efficiency that we thought we were getting. So yeah, that's just an example of how we've not been very good at policing fossil fuel standards. We've had very poor renewable subsidy strategy, and subsidies, I must tell you, are always a disaster in my view. Many of you will probably remember the Common Agricultural Policy and the criticism of using one subsidy to fix another. We're basically in the same situation now, because we are subsidising fossil fuels in various hidden ways, and we're having to use then highly visible subsidies to renewables to try and counter that. Of course, it's very easy to poke a stick at the renewable subsidies because you can see them all. Very few people can see where the hidden subsidies to the fossil fuel segment is being provided. We've had pretty poor consumer awareness. Very few people realise, first of all, that they own a heat pump already, and even fewer people recognise that the gas boiler or oil-fired boiler, if you're off the gas grid, or LPG, actually are contributing to emissions in the UK. A remarkably high proportion of people had no idea that their gas boiler was contributing to carbon emissions and other greenhouse gases, because under the latest iteration of the Committee on Climate Change's advice to government, we have moved from measuring carbon, so the target was 80% reduction in carbon emissions, carbon equivalent emissions. The target is now 100% decarbonisation, but it's actually no longer just carbon, it's now all greenhouse gases, which is obviously that much more demanding. The other thing which many people, I think, don't realise is that the burning of natural gas generates NOx and SOx, so nitrogen oxide and sulfur dioxide. And it's the NOx, the nitrogen dioxide, which actually causes damage to people's health. So in terms of looking at air quality, it's not just vehicles. The burning of gas, particularly in urban environments, of course, where you have the concentration, which is causing a massive problem. So there's a number of reasons why we should be looking to get away from combustion. And then the last point is that we've got pretty poor skills in the heating industry in the UK, because we've allowed our heating sector to deploy fossil fuels pretty badly, because no one's been measuring the quality of the outcome. So we've lost many abilities that we should have had, even in the fossil fuel segment at the moment, which we're going to have to retrain. But we've got a plan to do that, so it's okay. What's driving electrification? So very quickly, this graph shows you what the outcomes are going to be from various heating technologies. So the black line across the middle, that is a gas boiler, and that runs at the carbon factor of natural gas, which is obviously a fixed figure. The yellow line, the pale line at the top, that is combined heat and power, gas combined heat and power. For those of you that don't know, a CHP engine delivers both electricity, generates electricity, and also heat. And the idea is you capture both and you get the benefit of both. The reason why CHP is becoming less carbon efficient, i.e. more carbon intensive, is that as the carbon factor for electricity drops, the value, the carbon factor of the electricity you get from the CHP engine, which is burning gas, goes down, and so it becomes more carbon intensive. The lines at the bottom show the gradual reduction in the carbon emissions from different types of heat pump. But you can see that there is every chance that we're going to get down pretty well to zero by 2050. The little block on the right hand side of your screen there is a snapshot taken from a GridWatch application which sits on the Ground Source Heat Pump Association website. It takes real-time electricity generation data in the UK and converts it into the outputs, the carbon outputs for different heating technologies. So this snapshot was taken on the 6th of July at 2:30 in the afternoon. So obviously, high summer. The national grid at the time was running at 118 grams of CO2. So the bottom green bar there, 118 grams of CO2 per kilowatt hour. If you were putting that electricity into a heat pump, ground source operating at 4:1, which in a new build environment it should, ground source in a pretty averagely performing retrofit scenario operating at 3.2:1, you can see that your gas boiler running at 85% efficiency, putting out 215 grams of CO2 per kilowatt hour of heat delivered. The heat pumps are down at 30 and 37. So we're already getting a massive reduction in carbon emissions. 118 is quite low by today's standards. The average at the moment in the UK is probably about 233 grams for the national grid, but it is falling all the time. Every time we bring more PV online, more solar, more wind online, that figure's dropping. So to heat pumps at last. I know you were thinking, when's he going to get to the heat pump bit? Okay, so here it is. So heat pumps 101. For those of you that want to know what a heat pump is, and this is your fridge. So the bit on the left-hand side that shows what is a loop going into the ground, that is your fridge, if you like. And the bit that looks like a radiator, that is the back of your fridge. So the ground bit's inside your fridge. The radiator is the back of your fridge. If you put your hand behind the fridge, you'll feel it's hot. So we're just running a heat pump in the opposite direction. So what we've got inside the box is we're harvesting some low temperature environmental energy, either from the ground or from the air, doesn't really matter how we're getting it, and we're using it to apply some heat to the evaporator section of the heat pump. And in the evaporator, we are boiling the refrigerant that's sealed inside the heat pump and turning it into a gas. And we then put that gas into the compressor, which is the heart of the device. It's where we use all of the electricity pretty well. And you'll remember, I hope, from your schoolboy and schoolgirl physics, that you can't compress a solid and you can't compress a liquid, but you can compress a gas. And when you compress a gas, it gets very hot. So what we do is we compress this gas that we've boiled, because the refrigerant boils at about minus 15 degrees. So anything we bring in from outside that's more than 15 degrees, more than minus 15 degrees will boil the refrigerant. We then put that gas into the compressor and we compress it, and it gets very hot. And on the condenser side, we are then harvesting that very hot temperature energy and putting it into underfloor heating, radiators, hot water cylinders, whatever you choose. Obviously the gas is cooling because we're taking some of the heat out of it. It eventually goes to the expansion valve, we take the pressure off, and it returns to its liquid state, and then we boil it again. So it's just a continuous cycle that's going around. So that's what's happening inside a heat pump, and that's how we get from low temperature source side to high temperature delivery side. And I say it's exactly what's happening in your fridge at the moment, in the opposite direction. If we think about how you measure the efficiency of heat pumps, what we're looking to do is to put in a unit of electricity to run the compressor and expect to get out of it more than 1 unit of thermal energy. So if you run an electric bar fire, you put in 1 kilowatt hour of electricity and you get 1 kilowatt hour of heat out broadly. A bit less because it's not quite 100% efficient, but broadly it's 1 to 1. In a heat pump scenario, we are aiming to put in 1 kilowatt hour of electricity to the compressor and get something between 3 and 4, or even 5 in some cases, kilowatt hours of thermal energy out the other side. So it's a massive multiplier, and those additional 3-4 kilowatt hours of thermal energy are what we're harvesting from the environment, either from the ground or from the air. And in the UK, ground source tends to be more efficient if you're comparing like for like quality, because the source temperature in the ground is relatively stable through the year, whereas of course the source temperature in the air is seasonal. And when you need heat most, your air source temperature is obviously that much lower. So fundamentally, like for like quality in the UK climate, air source is usually 20 to 25% less efficient than ground source. Clearly lower cost, much lower cost to put in, but more less efficient. We've talked about the relevant difference in utility pricing. So, when you're thinking about comparing gas electricity prices, electricity is, for most people, about 4 times more expensive than gas, maybe 3, depending on your tariffs you're on. So we've got to run a heat pump at 3 to 4, an efficiency of 3 or 4, just to get cost parity with gas. And this is the fundamental reason why we're not running a lot of heat pumps here already. In Sweden, by comparison, the gas and electricity price is pretty much the same, and not surprisingly, 90% of Swedish homes are heated with heat pumps, because there is a huge incentive to do so. The other thing to mention at this point is that for those of you that are burning oil, so anybody from sort of outlying villages which don't have access to natural gas, oil and LPG are probably the default. The village where I live is pretty well all oil. We are, I think, going to start see government moving against oil. In the Clean Growth Strategy of 2017, there was a statement that they wanted to remove oil from the national heat mix by the end of the 20s, so by 2030. I think that with the increasing climate pressure coming on, we're going to see movement against oil relatively soon. I think it'll have to come with some form of targeted support, but anybody who's burning oil at the moment, be prepared for some movement on oil. The default would be to move to LPG, bottled gas, but LPG is obviously significantly more expensive than oil at the moment. Oil price, of course, highly volatile. And then the other thing to just bear in mind is that you could combine running a heat pump with running some solar PV. So if you've got solar PV, you're generating electricity, you could use that to run to partially run your heat pump. The problem is, of course, your solar PV output is at its lowest in the winter when you want to run the heat pump most, unless you're in the fortunate position of running your heat pump to heat your swimming pool, in which case it's probably a perfect fit. And so back to my correlation with electric vehicles, we are in a situation where battery storage, either for PV or for off-peak electricity, and thermal storage, which we use when we run a heat pump off lower cost electricity, both of those forms of storage need to be considered in the round. Thought it was worth letting you see what some heat pumps look like. So the devices on the left hand of the screen there, those are about the size of an upright fridge, to give you a feel. The one on the extreme left is a twin compressor unit. You can see there are 2 devices stacked on top of each other. They're all in one box, but effectively that's 2 heat pumps. They're a sort of much larger domestic property. The next 2 are more domestic scale, sort of average household scale. And there you can see you've got a heat pump device in the bottom. So that's the compressor and the 2 heat exchangers and expansion valve and what have you. And then above you have 2 types of cylinder. In one of them you have a what we call a thermal store, which is not potable water, but you can use it to heat potable water instantaneously. Potable is the water you get out of your taps that you can potentially drink. So in that instance, off this top coil, we are taking the hot water instantaneously. So it's just like a combi boiler in that respect. The other device, actually, that is a hot water cylinder. So that's storing hot water in the same way that your cylinders if you have them now. If you're not on a combi boiler, you'll have a hot water cylinder somewhere in the airing cupboard, exactly the same effect. At the bottom, the one in the device in the middle, that's about the size of an under-counter washing machine. Again, that's sort of domestic scale heat pump. And then we've got a couple of air source examples. The twin fan unit, obviously a bit bigger capacity. The other sort of standard domestic. And to give you a feel for size, well, we've got some photographs coming up of them in situ, so you'll get a feel for the size in situ in a moment. So, you know, where are we going to put these devices? Well, the air source machines, clearly the external unit, and we have some that are monoblock. So the device on the bottom right, that's a monoblock. So everything is in one unit. It's a mono unit. So that's the heat pump, the fan, everything all in one unit outside. The other air source device, that is just the evaporator on the outside, and then inside there's a unit which has the compressor and what have you. So that's referred to as a split system. You can see the scale of them against the buildings. And then the other two images show a couple of ground source installs. One is very small. You can see the top left, that's a shoebox, known as a shoebox unit, designed for small apartments. And you can see it's got a small hot water cylinder stacked above it, but it's effectively in a broom cupboard. The other image shows one of those upright fridge type units sitting in a kitchen, in a utility room, and the cabinets are highly acoustically insulated, and so putting them inside, they're designed to sit in utility rooms, in kitchens quite happily, and they sound just like a fridge. So it's just like having another fridge in the room. One of the other questions we're frequently asked about is emitter type, and you may have heard comments that say, oh, heat pumps only work with underfloor heating, you've got to have low temperature flow, you've got to have highly insulated buildings. All that, I'm afraid, is baloney. I can give you a heat pump that will do 120 degrees if you want it. It will be less efficient, absolutely, I accept that, but it can be done. Please ignore any of the myths that you've heard about not being able to use heat pumps in hard to heat buildings. I've made my career as an installer. I spent 10 years as an installer, largely working in listed and period buildings. So we were putting heat pump systems into listed buildings. National Trust has got a huge fleet of heat pumps. They've realised that people don't want to particularly burn trees anymore. So we can use any type of emitter. So underfloor heating clearly is great because it tends to operate at lower flow temperature. And the lower the temperature we ask the heat pump to make, the more efficient it is. So it's ideal if we can reduce the temperature, but it's not essential, and I will describe why in a minute. We can use standard panel radiators. You can see the bottom left there, standard panel radiator. Top right, sectional, that's a modern version on the sectional cast iron radiator. Again, if you've got old cast iron radiators, if you're lucky enough to have lovely cast iron radiators, fantastic. As long as they're sized appropriately, we're fine. The bottom right, trench heating, and the unit in the middle is a fan coil, which many of you may not be familiar with, but it's exactly what you see in the ceiling of shops and what have you. When you look up, you see those grills in the ceiling. That's a fan coil. We're not very used to having such devices in our homes in the UK at the moment, but on the continent and certainly in places like New Zealand, fan coils pushing out warm air is a very common way of heating space. So the question about flow temperature is an interesting one, because whilst I accept that when we are putting 50, 60 degrees into radiators from a heat pump, it is less efficient. We will be running that heat pump what we call weather compensated. That means that the temperature that we ask the heat pump to make will depend upon the air temperature outside, i.e. how big are the losses in the building. So the more the losses in the building, so the colder it is outside, more the heat losses, the higher the temperature we have to put into the emitter, whether it's a radiator or underfloor or whatever. But what I would say to you is that the number of hours a year for which we have to use the highest temperatures is very small. 30 hours, I mean, how long do we spend below zero in the UK climate at the moment? Not a lot of time. It gets all the headlines, of course, because it causes a problem. But from a domestic heating, home heating perspective, it's a very short space of time. So if we're running the heat pump hard for only 30 hours a year, the impact on the overall efficiency throughout the year is modest, and there are many other factors that will impact on the efficiency, that can impact on the efficiency rather more. So the issue of flow temperature is not quite as important as many people think. And of course, it's in the interests of the gas lobby, the green gas lobby particularly, to promote the concept that you can't have a heat pump in a building that's hard to heat, or unless you've got underfloor heating, because clearly they don't want to see heat pumps succeed. But please be reassured, you can put it in anything. We can use high temperature heat pumps, so we have special devices that will give us higher temperatures, 80 degrees out of the box. And if we need to, we could deploy them in what we call hybrid, in a hybrid configuration, where you combine a heat pump with a fossil fuel boiler. So if you for whatever reason you can only put in either an undersized or a low flow temperature heat pump, and you need to be able to supplement it, we can deploy hybrid systems that will allow us to do that quite happily, and you'd still get the majority of the carbon benefit, because you'd only be calling in that fossil fuel support for a small number of hours a year. And there's also frequently discussion about hot water. In other words, if you can't get hot enough hot water out of a heat pump, well, it's a brave person that stands under a shower at more than about 45, 42, 43, 45, 45 is very hot. So 40, 42 degrees. So we traditionally store water at 60 degrees in the UK or thereabouts. Many of you can look at the thermostat on your cylinders, when you go upstairs tonight, see what they're set on. But they're probably set on 60-ish. Some people might turn them down a bit to 55 now. It's all about looking at storage volume, because clearly if you're storing at higher than 45 degrees, you're going to use cold to mix down to get to usable temperature. And the less cold you have to use, because you've got a lower storage temperature, the more you have to store. So in our world, cylinders get bigger, but we're storing the water at a lower temperature, so we have lower losses. The heat pump's more efficient. There is a question about Legionnaire's disease, and whilst it was the case years ago that with lots of dead legs and what have you, there was potential for Legionnaire and hot water distribution systems, that has largely been resolved. And now the biggest single source of Legionella infection in the household environment is probably your shower heads, because that's where warm water will sit for a period of time. Doesn't mean you have to panic about it. I cannot recall the last time someone caught Legionnaire's disease in a domestic environment. You're more likely to get it from the windscreen washer on your car, to be honest. And there's no regulation on hot water in a single dwelling. So there's nothing to point to. And what we would tend to do for best practice is say that once a week we will engage in immersion, and we'll elevate the temperature in the cylinder for an hour to above 60 degrees and run that as what we would call a sanitization cycle. Building types, again, just to reassure you all, it doesn't matter what type of building you've got. Everything can be made suitable for a heat pump. There is a heat pump system that will suit everything. So top right, new build, top left, new build, highly efficient, of course. That's that particular unit. That's got a ground source system in it with 3 boreholes in the front drive. The bottom left, that's a rebuilt barn conversion. Actually, the barn was taken down, moved and rebuilt as a dwelling. You can see that's got a pair of air source heat pumps heating the whole of that building. It's quite a substantial building. The manor house on the top right there leaks like a sieve. That's operating solely on ground source quite happily. And you can see a twin fan unit on a relatively new build. That's a bungalow, happens to be a bungalow on the bottom side. So any building type you like. The impact on things like sharing resources between buildings, what it does is it introduces legal issues in terms of selling buildings on. But if you've got buildings that are always connected, blocks of apartments, for example, then potentially one can get better economies of scale by combining units, either by having multiple individual units in each flat, which you connect to a shared ground array, or by having a much larger consolidated plant room. So there can be some economies of scale, but in a single domestic environment, you're thinking about your own homes, the idea of tying them to another property does complicate things from a legal perspective when selling. The design should be engineering led. At the moment we have these subsidies, so we have the renewable heat incentive, and there are other schemes coming along. You'll have probably heard about the latest Green Homes Grant. All of these tend to queer the pitch for engineers to design the best possible system. So I would always try and encourage you to go for the best engineered solution first and see how that can then be optimized for any assistance that's available, rather than the other way around. We have some issues with planning consents, not a lot. Ground source and air source both have permitted development rights for the vast majority of domestic installs in the UK, up to 45 kilowatts. And to give you a feel what that means, the average home in the UK, average bear in mind, is probably something in the region of 10 to 12 kilowatts. So 45 is quite a large home. The only thing with air source is that we have this issue about the noise, because clearly there is some noise outside, and there are regulations within the microgeneration certification standard, which if you meet those requirements, then you will have permitted development rights. So not to worry too much about consents. A quick piece on the carbon emissions impact. So this little spreadsheet is one that I use to put in so that top yellow figure, that's the heating demand for the house, heating and hot water, 15,000 kilowatt hours a year. The heat pump efficiency, in this instance, we put in at 3.5, so we're going to use 4,343 kilowatt hours of electricity. The red line, these are the carbon factors that are currently attributed to primary fuels using figures from DEFRA. And you can see there the electricity figure is 233, which is what I think is about the average at the moment. And the other carbon factors for the other fuels. You can see then that if we're running our heat pump at 3.5, the last column there shows you the carbon savings with the heat pump running at 233. And you can see that natural gas, we are already showing savings of nearly 70% against natural gas, oil nearly 80%. And of course, if the grid continues to decarbonise at the rate it is now, you can see those savings going up massively. And all heat pumps are zero emitters at the point of use. So these emissions are at generation level. What it also means is you're not getting the NOx and the SOx and the particulates at domestic level. So your towns and cities are being cleaned up from an air quality perspective. Here's a little piece on what we think some of the key factors are for homeowners. So what are the considerations that would go through your head if you were thinking about putting a heat pump in? So there's this question about fossil fuels work. We're told that boilers are great. Well, do we really know how efficient our boilers are? We've got this resistance or fear of change. Well, I tell you, you've already got a number of heat pumps, so actually there's nothing to be frightened of. There's nothing to be resistant to. We value energy very poorly in the UK because gas is so cheap. Most of us don't really value energy that highly. It's why we find it very difficult to get people insulate their homes. Very difficult. It used to be very difficult to get people to put in loft insulation, even when the materials were being given away for free. So we need to improve the way we value energy. Capital cost of change is the big one. Clearly, moving to a heat pump of any sort is significantly more expensive than replacing your fossil fuel boiler. And we have the operational cost. This is back to the spark gap, in that you've got to be running a heat pump very efficiently on standard tariff electricity in order to be able to compete with particularly gas. And there's just general knowledge and understanding. People are not yet very well aware and attuned to the electrification of heat. On the positive side, we've got the environmental attitudes. We've already talked about Sir David Attenborough and Valletta, and the intergenerational pressure. We've got some regulation beginning to come through. So MEES, that is the minimum energy efficiency standard, which applies to rented properties. So if any of you have got buy-to-let properties or anything like that, MEES would apply. And we have building regulations changes coming up. So in Q1 of next year, we should get a new version of building regulations, and that will reduce the carbon factor of grid electricity in the SAP process, and it's SAP that we use to check the sustainability of new buildings, and that will eventually get us on a pathway to actually building much better buildings. We have government subsidies at the moment. Subsidies actually have not been good for our industry, but clearly if you can get onto them, it's a very good option from a domestic perspective, and I've got a little work example in a minute which I'll show you. And you know, it's a better offer. We can, with electricity, we can give you a more controllability. We can give you access to the controls over the internet. You can control individual rooms, zones. You can do all sorts of things because it's much easier to control electric devices than it is to control the burning of any gas. And we have a transitional approaches, so this hybrid. So anybody who's concerned, you can retain a gas, you can retain a fossil fuel boiler, put in a heat pump. You've always got that fallback scenario. I've used that in my installer days frequently to allow people to feel more secure. I'm really conscious of time now, and I want to leave plenty of time for Q&A, and I'm quite happy to run on. If you are, I'm happy to run on, so please don't feel constrained. Little quick work example on the renewable heat incentive. So average family home, that's actually quite a good sized family home, 150 square meters, about 7.5 kilowatts peak, 16,500 kilowatt hours a year, with an air source unit running at an average of 2.8. So that's our factor, that is our translation from the amount of electricity we put in to the heat we get out. Ground source higher at 3.4. You can see the subsidy values are based on the tariffs. So subsidy value for air source, 1,500 a year. Sorry, 1,150 a year. Ground source, 2,465 a year, and that is obviously a reflection on the fact that it's much more expensive to put the ground source in. You can see that it's potentially twice the cost of putting in an air source unit, and that's largely the cost of the in-ground collector. Well, you have to bear in mind, of course, the in-ground collector has a lifetime of probably 100 years, so it's a massive investment. You're effectively buying your fuel for years in advance. And with the Green Homes Grant, which obviously has been quite a bit of publicity and is due to come into force, applications should be open soon, you can now get a grant of up to £5,000 to contribute towards a heat pump system, up to 2/3 of the cost of the heat pump system. Where this does have real value, I think, is that you can take the grant to assist with the capital cost and then claim the domestic renewable heat incentive. Yes, the value of the grant is recouped from the incentive because you can't double dip the public purse, but it does mean you get the capital contribution up front, and then you just get reduced payments over 7 years. So that actually is potentially quite useful and could allow some people to choose to go to a more efficient ground source rather than air source if that's what they want to do. A quick glimpse of the future. So this relates to this energy storage question. So many of you will be familiar, and you're going to hear about electric vehicles I hear in a couple of weeks, so perhaps I'm preempting here, but the concept here is you charge your electric vehicle overnight on a low-cost electricity rate. It's the same principles applied to night storage heaters. We can do exactly the same with thermal storage. So the two devices on the there, you've got a cylinder of hot water, which is a very simple thermal storage device. The other rectangular device, that's a phase change battery, and you can store very crudely 4 times the volume of energy in a phase change material than you can in water. And the value of this is shown in the graph above. So this is a piece of data taken from Octopus Energy's Agile tariff, which is their primary tariff for EV users. And the orange line shows the profile of a standard electricity user. So their peak demand is between sort of 4 and 8 o'clock in the evening. The Agile tariff peak is the green line. You can see that by allowing people to charge their electric vehicles overnight, the peak has been moved. We've reduced this peak, which is the maximum generation peak that we need to reduce because that's when most households are using their electricity. And this electricity, whilst it's low cost, it's not a straight line relationship, tends to be lower carbon too. So that's the real value. And we can do exactly the same by running heat pumps on those same sorts of tariffs and storing the thermal energy. Current policy just a very quick one here. Evidence suggests that we've no idea what the government's really thinking yet. There is no long-term plan for energy at the moment in the UK. We haven't got an energy white paper yet, but it's due this winter. We are waiting for the heat and building strategy. That's due in the autumn. We're waiting for the update to building regulations and the new future home standard, which should come in 2025. Building regs, as I say, we should get in Q1 next year. We've got an electrification of heat task group running at the moment, which is brand new, so government are beginning to take it seriously. We've got very low ambitions for domestic heat pump installation so far, so that needs to change. And we've got no effective strategy at all for non-domestic, so commercial heat pumps. So there's still a massive amount of current policy work to do. And you'll be very pleased to hear that that is the end. So I'm sorry I've run a bit. You can see it's a massive topic, but I'm very happy to take questions for as long as you like. And you can always fire them in afterwards. So please, if you don't get through them all tonight, please fire them in. Very happy to field inquiries, emails, whatever you want. So,
okay, well, thank you very much for that comprehensive talk, Bean. Can I just clarify? You said that the new green grants are going to offer 5,000 up front to the capital costs, but they're going to recover the money from the renewable heat initiative. So it's not really new money, is it? It's something, it's recycled money.
Well, some properties will not be eligible for the renewable heat incentive. So in that instance, you get the value of the capital grant. What you can't have is both. So you will...
Well, why can't you have both? There's no reason why the government couldn't legislate to allow you to have both.
Well, there's an overriding principle in government that says that you can't double dip the public purse, and they're effectively saying here you would be double dipping the public purse. It's a principle that's been knocking around in energy terms for years, and it actually applies to pretty well everything. So there are debates about double dipping in terms of subsidising electric vehicles. There are a whole load of potential areas where double dipping taxpayers' money is potentially a risk, and this is what they've chosen to do. So I think that the fact that those who need the help with the capital cost can get it and then have reduced subsidy does help to some extent.
Okay.
As I say, I'm not a great. I'd love to get to a point where we actually install these things because we believe we should,
okay,
and because it makes good sense to do so financially without any type of interference. And the way we do that.
When is gas boilers new being phased out?
So at the moment, the expectation, and it is only expectation at this stage, we're waiting for the future home standard to be published. The expectation is that there will be no new gas connections into new build properties from about 2025. So it's still some way off. And that only applies to new build. So it wouldn't stop you replacing your gas-fired boiler in your own home, for example. That is not yet currently on the cards.
One more question.
But I must tell you that those of you that are burning oil at the moment, if anybody is, I think that it is absolutely on the cards that we will get to a position where you won't be able to replace your oil-fired boiler relatively soon. And when I say relatively soon, I don't mean next week or next month, but within the next 2 to 3 years, possibly.
Okay. One more thing. What about the soil? Does the soil make a difference to the length of the tubing you have to have for a ground source heat pump?
Absolutely, it does. Yeah, and I'm sorry that time didn't really permit a detailed discussion about the in-ground collector array. So soil conditions, if we're able to go, if you've got enough land that we can go out horizontally, soil conditions absolutely make a difference. And if you don't have sufficient land and we drill, so we're drilling vertically, then clearly the geological conditions also have an impact. In terms of horizontal arrays, if you were to give me a genuine floodplain or a redundant watercress bed where there's lots of water moving through it, that's really good. If you live on the top of a hill where you've got a big layer of sand, and there are some parts of the UK where that happens, dry sand, bone dry sand, is a very poor thermal conductor. So in those instances, you would have to put in a lot more pipe in the ground than you would if you had genuine, relatively waterlogged soils.
Just we're on chalk here in the Chilterns. What's the situation with chalk? I've been told it's not a very good retainer of heat. Is that right?
Yeah, so bone dry chalk is, again, pretty poor. So if you are trenching horizontally and and we'd normally put the pipework about 1 metre below the surface. So if you have less than 1 metre of topsoil and you are into the chalk, you're bucketing the chalk,
Yeah.
then you would need to put sand blinding in the bottom to protect the pipework from any flints that might be in the chalk. And again, you would have to allow for the fact that the chalk is a poor thermal conductor. So, and it's also highly porous at the surface. So any rainwater will flow through very quickly and you won't get massive thermal advantage from rainfall, because the recovery mechanisms for ground in the UK are clearly solar gain. Sun comes out, warms the ground. Rainfall is the second recovery mechanism that we look at. So everybody gets rainfall. The average temperature of rainfall in the UK in the southern half of England is about 11 degrees. So if you've reduced the ground temperature to below 11 degrees by taking the heat out to heat your building, and it pours with rain, it's like having an oil tanker come up your drive, effectively. And the third mechanism is migrating groundwater. And here we're back to my floodplain or my watercress bed. So you've got water moving through the ground, and that's taking away the coof which you put in the ground when you take the heat out and bringing fresh thermal energy. Not everybody has that. So everyone gets solar gain, everybody gets rainfall, but the rainfall is more or less effective depending on the soil conditions. Not everybody has migrating groundwater at surface level. And much the same applies if we're drilling. So we drill into the chalk. At some point, we will hit the chalk aquifer. And the key is to understand where the aquifer is, because the more pipework we have at depth that is in saturated chalk, the more effective it is. So I looked at an example up above Hemel Hempstead, up near the golf course above Hemel Hempstead, and there it was top of the chalk hill, bone dry chalk. The driller had identified that the water level was down at about 90 meters below ground level. He drilled 12 boreholes down to 70 meters each. So he knew that he wasn't in the saturated chalk. And not surprisingly, that system didn't work very well. What he should have done is drilled a much smaller number of much deeper holes, so that a significant proportion of the pipework was in the saturated chalk.
So we have a question here from Trevor. What about licenses for ground source water usage?
Okay, so in most domestic scenarios, we would usually be deploying heat pumps in what we call closed loop configuration, where we put pipework in the ground, we circulate fluid, thermal transfer fluid through that pipework. Some people call it glycol. And so we're not actually making use of any water. So even if we're in the aquifer, if we've drilled into the aquifer, we're putting pipework in, we're not removing water from the aquifer. In some instances, it could be worthwhile using what we call open loop technology, where we would drill into the chalk aquifer and pump the water to the surface, abstract the energy, take the energy from it at the surface, and then put the water back down. In that scenario, you as the landowner are entitled to take up to 20,000 litres a day without an Environment Agency abstraction licence. 20,000 litres will deliver something between 11 and 15 kilowatts. So it would do a sort of average home. If you've got something slightly bigger, you're almost certainly going to go through the barrier requiring a license. And licensing from the Environment Agency is quite a painful process. So unless you want the water for other purposes, where abstraction becomes viable for you for other purposes, most domestic scenarios will probably be deployed in closed loop. The Environment Agency currently has absolutely no sway whatsoever over closed loop heat pump systems.
So in 2010, I think it was, the Labour, or no, just before that, the last Labour administration passed a regulation that all new homes should be zero carbon in this country by 2015, and then the coalition government scrapped that. Did that have a big impact on your business?
Oh, massive, massive. So the renewable heat incentive, which clearly is meant to drive renewable deployment, the outcome from the initial conditions for the incentive program, largely around huge over rewarding, first for solar PV under the feed-in tariff regime, and then for biomass under the RHI regime, meant that the size of the heat pump market halved in the space of about 6 months. And the tragedy was that under the previous program, which is, if anyone can remember, the low carbon building program, ground source heat pumps outsold biomass 2 to 1. So you can't tell me that all of a sudden there was some sort of light bulb moment and everyone realized biomass was more efficient. The fact is people followed the money. And what we're now seeing is a significant number of people with biomass systems, not so much domestic, but particularly commercial systems, where they are coming along and saying, actually, we want to get rid of this biomass. We want to convert it to some form of heat pump system, because the price of pellets particularly is volatile, like the price of oil. And they're finding that the maintenance requirements, again, more for commercial systems than domestic, the maintenance requirements are very significant. So this is the whole point about being engineering led rather than being led by the subsidies. So you should really try hard to be led by best engineering practice and then optimize the subsidy position, rather than being led by the subsidies and then hoping that you get an engineering outcome that's valid.
So, Dave, you've got a question. Did you want to ask something? Dave Faulkner, are you still with us?
Yeah, I am. Well, I put it in the chat there. It's just to move on from, it's nice to hear that retrofit possibilities are many and can suit most applications. Just a slight concern that how do we find out which is the best engineering design when, best we're in the world, most suppliers will push their own kit and their own design, and rather than telling you you'd be better off going down the road and getting an air source, or go down and get a ground source, or have a split system here and all that, how do you get the right design when somebody's going to sell you what they make?
Yeah, that's a very, very valid question. And it's one that, the industry, those of us that want to see best practice applied everywhere, do wrestle with. And I'm afraid to some extent, we can regulate and we can put in place standards. We can have trade bodies, and I would like to think that most practitioners who take the trouble to become members of their trade bodies will be trying to do the right thing, even though some of them may fail from time to time. But there has to be an element of buyer beware here. So what I would suggest to anybody who's thinking about putting in a domestic heat pump system of any sort, doesn't matter whether it's ground source, air source, hybrid, and having no idea which to start with is not a problem. The key is to do the research, talk to the trade bodies if you wish. We will always take inquiries. We have Ground Source Heat Pump Association already has a technical inquiry line available by email off the website. The new Heat Pump Federation, once the website goes live in sometime in October, hopefully, will be running the same. So pose questions, and look for people who have already done it. Take some advice from people who have done it. You will increasingly find that somebody someone in your circle may have done it, and then eyeball the installers. Get them in front of you. Do you trust them? Are they going to look after you? Take up references. Go and look at some reference sites. I mean, we are still at that phase in the market where you do have to do a degree of due diligence, I'm afraid. And it's really important that you make sure that you are getting into bed with somebody who, A, you think you can trust, and B, someone, we have a saying in our business that says you're much better off having the finest installer with the worst piece of kit than the finest piece of kit and the worst installer, because the worst installer will turn the finest heat pump on the planet into an immersion. whereas the finest installer will be able to do something half decent with a very average piece of kit. Now, by and large, most installers, certainly those of quality, will have chosen to work with a very small number of manufacturers' hardware. Now, that might sound limiting, but actually what it means is that they develop expertise. And the same applies in fossil fuels. Most boiler installers will work either, they'll find they're a Bosch man, or they're a Valent woman, or they're a Wasteman, outlet. So most of them would have made a principle of working with a single provider. What that means is that they develop expertise, and it's exactly the same in our world. So you want to look for installers whose engineers are factory trained. They've been to the factories to be trained on those particular devices. So there are some precautions. We are currently producing some consumer guidance, so procurement guidance for individual consumers. We're developing something, but we're also part of a consortium run by the Energy Savings Trust, which is working on a comprehensive set of consumer guidance. That probably won't be available till next year. I'm hopeful that we'll have something which will be a starting point for that available before the end of this year off the website.
The key factor surely is that you don't get the renewable heat initiative unless the installation is put in by someone who's micro-generated certified.
Correct.
So, do you have a list of people who are certified? So
the MCS website, the Microgeneration Certification Scheme's own website, has a list of installers who are certified. The GSHPA website, has a list of installers that are members of the association, and obviously many of those are common to both lists. And then many of the heat pump manufacturers run their own program of either approved, certified, VIP, various terms used, of installers. Now, bear in mind, there's very rarely technical assessment there. Most of that is based on experience and the level of devices, the number of devices they're buying per annum off that particular manufacturer. So treat that one a bit more carefully. But ideally, I think you would be looking for an installer who is definitely MCS certified.
Yeah.
Definitely a member of a trade body, whether it's one of ours, or there is also a heat pump association, which is largely air source manufacturers, and ideally someone who is on a manufacturer's listed website listing of preferred installers, and then take all those other precautions so that you would take if you're buying something that's where it's still relatively niche.
Okay, well that's been really interesting, and we're all extremely grateful to you for giving up your time to educate us all about.
John's been waving his hand all evening.
Has he? Well, there's nothing on the chat going, John.
Whether he wants to ask a question or whether he wants to cut us off dead, I'm not sure.
Go on then, John, carry on.
Oh, I just wanted to mention in the chat, presumably everybody's had a good look at the chat, there is a message there from Matthew Archer, who is from the Low Carbon Workspaces Grant Scheme, who is mentioning there are £5,000 grants for commercial installations. And I emphasise commercial, this is not domestic, but it is a good thing to know, especially if you run a company or you work for someone who you may be able to twist their arm.
Yeah, I think you'll find that there are a lot of regional assistance grant monies available to businesses. So we do quite a lot of work with Coventry Council. They have a whole program of grant assistance. And if you want to, again, we're back to this sort of double dipping of the public purse issue. If you want to be able to benefit from the non-domestic RHI for commercial schemes, there are ways of ring fencing that money. So you can potentially get grant funding from a local authority to do all of the due diligence, all of the feasibility studies, all the preliminary works, the enabling works, and then take the subsidy against the actual installation. So there are a number of ways that you can potentially combine other sources of funding. So definitely worth looking at what your local authorities are doing for commercial applications. Absolutely. So yes, that's very good. That's a very good point to make.
Okay, well, if that's satisfied everyone's curiosity. Can I thank you once again and wish everyone a good evening?
You're very welcome, and please come at us again with questions afterwards. And if you're going to circulate the slides, I will provide a PDF copy for you to circulate at will.
Thank you.
I think Trevor's got his hand up. Is he able to speak?
Well, I can't see everyone. That's the trouble. I only see the
Right.
people down the side. You have to put it on the chat if you want me to know about you. Go on then, Trevor.
That's right. Carry on. I'm happy to carry on as long as you like.
Yeah, mine's a question about the planning approval, because I've been in contact with us about putting an air source heat pump into the house here, and they've come back to me and said that I need to apply for full planning approval because I would need to have 2 units because of the size of the house.
Yeah.
So
They are right.
they're right.
The
Yeah.
permitted development rights pertain to a single unit. You're quite right. Sorry, I should have mentioned that. And it's very good that you've brought that up. The permitted development rights were written in 2015. The current version of PDR was published. And of course, it predates a lot of the further development in the way that we deploy these units. And there's a lot of inappropriate material buried in those PDRs, which we would really like to get rid of. We are in discussions with MHCLG, but of course, opportunities to rewrite legislation of that nature don't come along very often. So what we're trying to do is put in place what we want to see in PDR in the future, and then we've just got to wait for the next opportunity when the legislation comes up. But at the moment, you're absolutely right. If you need 2 units, you will need to apply for full planning.
Yeah, and that's what, so anything over about what, 16 kilowatts or something.
Yeah, so the biggest single phase compressors available at the moment will run up to something approaching 22-ish kilowatts. Air source units tend to have slightly smaller compressors in them because you're trying to control the size of the box. And one of the permitted development rights requirements is that the physical size of the box, the total volume, is less than a certain value. My personal view is that shows a complete misunderstanding of air source technology, because the smaller you make the device, the less efficient it's going to be. You want very big fans with low fan speed, and so physically the boxes should be big. If you look at the Scandinavian devices, they tend to be much bigger and they tend to be much more efficient. So there are lots of issues with PDR, but yeah, fundamentally you would need planning. But what you would say, of course, is that the local authorities have an obligation to reduce carbon in their turf. They would have to find some pretty good reasons to turn you down. It's an irritation, I accept, and it means a fee to lodge the application. But I would be staggered if they were looking for reasons to turn you down.
I've got a question, if it's possible.
Right, no problem.
I've got it in the on the chat as well.
Okay, John Perry.
Is that all right for me to continue?
Yeah, go for it.
Okay, well, we moved from a London Victorian terrace property to a house in Marlow that's only built in 2014 with all the insulation improvements and so on. It's also air pump heated.
Yep.
We're finding that it's actually very expensive. And we're wondering, I mean, obviously you've explained a lot about the gas and electricity costs. Do you think that would be?
So
I know you don't know our house, but it's a modern built house. It's all of that. So
yeah, but if we think about the principles at stake here, so your property in London, that was a terraced house?
It was.
And your property in Marlow is detached?
It's semi-detached.
Semi-detached. Okay, so in a terrace, of course, unless you're end of terrace, your heat losses are partly constrained by the fact that you're joined to people either side.
Yeah.
And you're burning gas, and as we know, the price of gas is relatively low. In your semi-detached new property, you have got the higher losses because you've now got 3 outside walls instead of 2. So potentially you've got greater losses, although I accept, new build, it should be that much more efficient.
Double glazed, etc.
Yeah, but you're finding it expensive to run. Now, it could just be that the house is much bigger, and because you're burning electricity now and you're used to burning gas, it is just more expensive. Obviously, as you say, I don't know the relative scale between the house you came from in London and the house you've gone to. But what I would suggest to you is that if you, was the house built new with an air source heat pump? Do you know, was it put in by
It
someone?
was, yeah.
Okay, right. So
It was actually a forward-looking builder who saw the regulations in 2012-13 and said, every house I build going to have an air pump.
yeah, well, I think that that's very laudable, and clearly to have an early adopter building firm is very good news indeed. What I think that perhaps you might need to consider is having a bit of analysis done to make sure that when he tried to do his best, he didn't end up buying an undersized heat pump. Because if the device is undersized, it will be thrashing itself very hard and trying to produce high temperature water all the time. And of course, that will drive it into the less efficient, its less efficient usage phase, because you're asking it to produce high temperature water all the time. There are occasionally other configuration aspects around the deployment of heat pumps, particularly inexperienced people, because in new builds, there is no requirement for MCS certified installers. The only legal requirement at the moment is for MCS is if you want to claim the renewable heat incentive. That is the only legal parameter for having MCS certification. We are beginning to see some of the national house building insurers starting to ask for it, but only recently. So it may be that the device was deployed by a plumbing firm rather than an MCS certified installer, that they misunderstood the technology, because a bit like Mercedes cars, air source machines, you sometimes have no idea what the number on it actually means. So when a device says it's a 12 kilowatt unit, that is frequently measured at an air temperature of 7 degrees. So when you get down to -2, that 12 kilowatt unit may actually only be putting out 8 kilowatts. So if they think the building needed 12 kilowatts at peak, i.e. design conditions, when it's -3, -4 outside, they bought a 12 kilowatt machine without realizing that actually, when you need it most, that unit will not be putting out 12 kilowatts. So there are some steps that you can take to evaluate the unit from first principles against the property you've got. And we could potentially take a start. So what I would suggest is that if you go to the Ground Source Heat Pump Association website, or you lift my email address off the slide, and if you send me the address and postcode, and you can take an image, a digital image of the plate, the identification plate on the air source unit, if you can find it on the back, if you can get a digital camera to take an image. I will have a quick look at your EPC for you. EPCs are not great, but I'll have a quick look. It will give me a feel. I'll have a look at the device plate and see whether I think that there is a significant risk that the unit might be undersized.
You have to have a SAP.
I'll quite happily look at that. I'll quite happily look at that for you. If there is a risk, then there are some steps that you would be able to take to determine that much more accurately.
Very much appreciated. Thank you.
John, can you take over chairing, because I've got to go up to London now. And people obviously want to carry on. So if you take over the chairing.
Yes, okay.
Thank
Robin,
you. Thank you very much.
Are there any more questions? I think we're getting to a close. We don't want to bore people or keep them for ages and ages.
I don't want people nodding off.
No. Anyone got any? Say one last. Yeah, Gareth Herford.
Hello. I just wanted to ask the current cost of well, I've got loads of questions, to be fair, Bean, but I'll choose one. The current cost is extremely high, I think, for like something to be rolled out into the average home. I just wondered, is there any chance of these costs coming down from manufacturers? Is it are the cost of the air source and ground source heat pumps so high because they're not used so much, and as they get rolled out?
What we have to bear in mind is that the UK market is a relatively tiny part of a global market. The reason why solar PV panels came down in cost so much is that what we were doing was generating an entirely new market. You know, solar PV was not being deployed at scale anywhere. And so when the solar PV market started to take off, clearly production ramped up globally and the price came down. Our problem is that we're currently installing between 30 and 40,000 heat pumps a year over here. They're installing them in the millions in Europe. So the price, and particularly bear in mind that a lot of heat pumps are coming in from Europe, the price of the boxes themselves does not have massive room for movement. Now, that doesn't mean that the price won't come down, because in the UK, clearly we have distribution costs, we have importing costs. If you're bringing in a trailer with 10 units on it, you've got a fixed cost. If you bring in that same trailer and it's now got 50 units on it, clearly you're amortizing your distribution costs across a great deal more devices. And so there are a number of costs that relate to the sale of the overall system that will come down. The other thing to bear in mind is that what you're buying is not, you shouldn't try and compare it to replacing your gas-fired boiler. So if you're moving from gas to some form of heat pump, it is not a like-for-like comparison to say, look, my gas boiler I could replace for £1,000, but if I want to buy an air source heat pump, it's going to cost me 7 or 8. Because in that system, you are buying not just the air source unit, you're almost certainly getting a new hot water cylinder. You may be getting a buffer cylinder of some sort. You're getting all new expansion vessels, all new valves, a whole load of new piping, and you're getting new warranties on everything, new circulation pumps, the whole lot. So actually you're getting a new system. So it's a bit like saying, I'm going to take out all my gas-fired systems, all the pumps, all the controls, all the cylinders, and replace those. You make that comparison, actually the capital cost isn't as drastic as you think, but I can absolutely see why people balk at the capital cost. And with the ground source, the additional cost of ground source, that's effectively, you're buying your fuel, you're buying your lowest cost fuel, and it is the lowest cost fuel if it's done well, there's absolutely no doubt about it. You're buying the lowest cost fuel that will last the lifetime of the property. And so, if you're intending to be in your house, if you bought your forever house where you're going to settle, bring up your family and you expect to be there for 20, 30 years, ground source is a fantastic investment. If you're in a house that you think will be moving on from in 2 years' time, probably not. So it is very personal, but I think that you've got to try and, when looking at the cost comparison, you've got to try and make a fair comparison. I know that doesn't make the capital cost any easier to bear, but I think that you've got to consider all the other bits that you're getting, because you're not just buying a boiler as opposed to buying a heat pump. You're buying all the bits that go to make the heat pump actually function. And what you've got to remember also is that when you come to replace the heat pump device, an average condensing boiler these days will last between 8 and 12 years. And the reason why boiler sales are going up in the UK at the moment by more than the number of houses we're building is that boiler quality is coming down. And because condensing boilers don't condense, the condensate runs back into the boiler, it's highly acidic, and it rots the boiler from the inside, and the boiler metal is getting thinner and thinner to make them cheaper and cheaper. So the lifetime expectancy of condensing boilers is coming down at the moment, whereas you see high frequency non-condensing oil-fired boilers that are 30, 40 years old. They're still chugging away. They're only 50% efficient, but they're still functioning, whereas you would never see a condensing boiler last that long. A good quality Scandinavian air source heat pump should do 15 to 18 years, and a good quality Scandinavian ground source 20 to 25. So you start building these factors into the total cost of ownership. If you are in the luxurious position of being able to look at total cost of ownership as opposed to snapshot capital cost, then I think you would rapidly come to the conclusion that investing in heat pumps does make sense already, even with utility prices as they are. And we have to accept, I don't think anybody would assume that at some point we're not going to get movement in carbon taxation against fossil fuels and in favour of electricity as it's increasingly decarbonised.
Okay, thank you. Look, we've run over nearly half an hour already. I'd like to draw this to a close. We are recording it for other people to see later on as well, and we don't want it to be forever. Can I thank everybody for attending? Great to see you all. Can I lastly thank Bean for an excellent talk, which I think has illuminated all of us into what heat pumps are all about. And can I remind you that in a month's time, 6th of October, we have got a similar event, Ask the Experts on Electric Vehicles, i.e. cars and electric bikes. So that should be interesting as well. But can I thank you all, especially Bean. And
I would also thank you for attending. Thank you for listening.
yeah, and I wish you all good night. Goodbye.
Thanks very much. Cheers, Bean. Thank you.
Thank you.
Cheers.
Thank you.
Thank you very much.
Gareth, if you've got more questions, drop me an email.
Oh yeah, what is your email?
It's on the screen at the moment. Can you still see it?
Oh yeah, of course it is. Sorry,
Yeah.
the chat box is in front of it.
Yeah.
Take
Okay.
it quick. Take it quickly.
Yeah, hpf.org. Right, I've got it.
Brilliant.
Brilliant.
Bye.
Thank you.
Thanks very much, everybody. Good night.
5, 4, 3, 2, 1.